If you notice, I have on the top of this page given you a quick multiple choice quiz to take. Sorry about the formatting. I thought I fixed it so that they were all in the right spot. And I obviously did not. So just real quick, take the quiz. And then I'll tell you what the answers are in just a minute.
Go with A's.
Is this the last page?
Where do we take it?
You just circle the answers on your test or on your notes.
Oh, it's in the notes?
It's in your notes, yeah?
But what are the questions?
If I wanted you to know the questions, I would have put the questions there. You're just...
Oh.
When in doubt, it's B.
Okay.
There's, oh, yep, there's a B. All right, that was easy.
Have you guys taken the quiz?
Yeah. Oh, and I forgot. I need a few more minutes. I got it right.
How confident are you guys feeling on this?
Super.
Super confident? All right, do you guys want to know what the answers are?
Yeah.
They are elephant,
Yes.
ellipsis, apple,
Yes.
collar.
Yes. Let's go.
How many did you get right?
3 out of 4.
3 out of 4? That's not bad.
0. So I chose the 1. Okay. Just bullet point.
I got 1. 2.
Okay. So, how many of you knew what the questions were? You notice I'm not even raising my hand. I used a random digit generator to get the answers. Okay, but let's pretend this was an actual quiz. What would you be interested in on this quiz?
The questions.
Like at the end, when you take a quiz in the class, what's the thing that interests you the most? What's the very first thing you look for when someone passes a quiz back for you? The grade. You want to know how many you got right. Is everybody with me? Okay. So, what are the possible number of correct answers?
4.
Yeah, 4.
Wait. There's only 4 correct answers.
Okay, but what are the possible scores in terms of how many correct you guys could get here?
1, 2, 3, 4, 5.
0, 1, 2, 3, and 4. If there's only 4 questions, you get more than... Right, so this is the number of correct answers. All right, and you guys, how many ways are there to get 0 correct?
4. 1. Wait.
1. In order to get 0 questions correct, you would have to miss every single one of them. Everybody good? In order to get 4 questions correct, how many ways can you do that? 1. Because what needs to happen on every single question? You need to get it right. Everybody with me? All right. Now, here's what we're going to do. Now, there's one way to get 0 correct, and there's one way to get 4 correct. Are those both equally likely? Just in your gut instinct. Are you more likely to get none of these correct?
No.
Or all of these correct?
I feel like it's not.
I don't think it's the same. Yeah. I think you're way more likely to get 0. So, are you guys with me that this has become a slightly complicated situation?
No.
Okay. All right. So, the tree diagram I put here, which by the way is to help you with the spacing, I built it for you, which I think is actually super cool of me. Yes?
Yeah.
Okay. Let's start filling it out. So, this first branch is the first question. What were the possible outcomes for the first question?
Yes or no?
So A, B, C, and D are your choices, right?
But like A or
Right or wrong?
But in reality, the outcome itself is, did you get it right or did you get it wrong? Is everybody with me?
Yes.
Okay, so I'm going to make an I and a C. Now, last semester we kind of talked about this. Do you remember putting probabilities on the branches?
Yes.
Okay, what's the probability of getting an incorrect?
0.75.
How many of the answers were incorrect?
0.8.
4 out of 5, yeah? Is everybody with me? So the probability on the first question that you got it incorrect is 0.8, and the probability you got it correct is 0.2. Is everybody with me?
Yes. Wait, how'd you do that again?
There's 5 questions, yeah? And how many of them are incorrect?
4.
4 out of the 5 options are incorrect. So the probability that you guess the correct answer is 1 in 5. Everybody good?
Yes.
All right. Now, let's say you get the first question incorrect. What are your possible answers for the second question? Incorrect or correct? Yes?
Yes.
With the exact same probabilities, because each of these had 5 choices.
They all have the same probability.
All the incorrects are going to be 0.8. All the corrects are going to be 0.2. And are you guys with me? And we can start filling this out. Oh my God, I'm exhausted. All right. And like we said, guys, what's interesting about each of these branches is how many correct. Essentially, that's what we would want to know. We want to know, first and foremost, what is our score on the quiz. Is everybody with me? So our number of correct answers. All right. So if I were to look at the first branch, which ends here, yeah? How many C's are in this branch? 0. So I'm going to put a 0 underneath it. All right, what about the next branch? Let's see, we have 1, and then all incorrects. Did you guys see the path I traced?
Yes.
The 1 correct, no, not correct, not correct, not correct. All right, so what I'd like us to do is at the end of each branch, write down how many correct is there. Okay. How do you guys feel about this? And if I asked you then, what is the probability of getting 0 correct?
0.8.
we would have, do you guys remember multiple events? What we do is we multiply probabilities over and over and over again. So we multiply probabilities down a tree diagram. So if I want to know what is the probability of getting 0, I'm going to go to the branch where we got 0 correct, which is this branch. Yes? Is everybody with me? And how do I calculate the probability of that branch? 0.8 to the 4th power. And what is 0.8 to the 4th power, y'all? 0.96? 4096. Great, thank you. How many would you expect to get right? 0.2 chance times 4 questions. Yeah, maybe 1. Okay, you guys. Here's what I want us to look at next. All right, next we're going to look at the probability of getting 1 correct. So I'm going to highlight 1 correct. And when we look at this set of branches, for this set of getting 1 correct, tell me about the probabilities we have. 0.2, we have 1.2 and 3.8. Is everybody with me?
Yes.
Okay. And then if I did the branch next to it, 1.2 and 3.8. And that kind of makes some sense. If you're getting 1 correct, you're getting 3 wrong. Is everybody good? And how many ways is this possible? Oh, look, 4. Okay, so if I want to find that probability, I would do 4 times 0.2 times 0.8 to the 3rd. Is everybody with me? When you look at all these purple branches, yeah? They all have 0.8 times 0.8 times 0.8 times 0.2. They're always 3.8s and 1.2. And all right, hence 3.8s and 1.2. So why did I multiply by 4? It's 4 different ways it happened. So each of these is a different outcome. This is you got the last one correct. This is what you got the 3rd one correct. This is that you got the 2nd one correct.
Okay, but how come for the 0
I'm sorry?
you can get 0?
Yeah, so it's the number of ways it could happen. How many?
Oh, because it's 0.
Because that is, you get 0 correct.
Oh.
We good now? This is a pretty complex topic. Wait, it's supposed to add to 1? What's supposed to add to 1? The sum of all of these probabilities, yeah? Yours doesn't add to 1? Hey, what did we get for this one? Did you get 0.4096 again?
Yep.
Okay. Okay. And you guys, for the 2,
So 6 times
4 times 0.2 times 0.8 to the 3rd.
Oh, okay.
How many different ways were there to get a 2?
6.
6?
And there's 2.2s and 2.4s. Pretty sure.
And what are we getting for that one? I bet it's smaller. 0.1356 or 1.5. And then 3's, how many ways does that happen? And then to get 3 correct, you would have 0.8 3 times and the 0.2 once, yeah?
Yeah.
3 correct, yeah. Thank you. What are we getting? Probably pretty tiny, I would think. 0.0256. And then last one, this would be 0.2 to the 4th, yeah? Which is
0.0016.
now, I would imagine if you add these together, were these the probabilities you got? And they didn't add to 1? They did?
Where did you get the 0.4 from under the 2?
You mean the 0.8?
Is that an 8?
Yeah.
That.
I didn't know we were.
No, I know. I just said, just add them together. Equal 1. That's great.
You can clearly see it's an 8.
Thanks, Charlie.
Now.
You guys, how would this have changed if there were only 4 options for each question? If there were 4 options for each question, the tree diagram would look identical other than the probabilities, yeah? 0.75 and 0.25 is what we would have, right? Are you guys with me? All right. So now, let's say instead of answering a multiple choice quiz, let's say I'm rolling one of my 10-sided die, and I want to know what's the probability of a 1 or a 2. Or what's the probability that, or how often are you going to get a 1 or a 2? Would this still fit on a 10-sided die? Would this tree diagram still work? Yeah, if we define it as you get a prize, let's put it this way. You get a prize if you roll a 1 or a 2, and you don't get a prize otherwise.
Yes.
Then would this diagram still work?
Yeah, there are only 2 possible outcomes if you're just saying you get it or not.
Exactly. Okay. And while making the tree diagram and all that kind of stuff is messy, do you get that it is programmable?
Yes.
Like, this is a known predictable distribution. It's not the normal distribution. We worked with normals a little bit. This is called the binomial distribution. Okay? And there are calculator shortcuts, right? Did anybody get all 4 right? How many of you got 3 right? 1 out of 11? How many of you got 2 right? How many of you got 1 right? That's the surprise one. And a bunch of you got 0 right then, huh? And if we had, like, I don't know, say 100 students do this quiz, right? Those probabilities will start to match. All right, so what makes it, in the probability world, we have known distributions that we can use to model things, okay? So in this particular case, we could model up to taking a 20-question quiz, 30-question quiz. The tree diagram would start to get really hairy. But do you guys see how predictable it is? Is this okay? All right, so conditions for the binomial distribution.
Wait, did we answer the bottom two?
I'm sorry?
Sorry, you flipped to the next page.
So yeah, because I thought maybe I just had a spacing issue, and then I decided I'm going to write out what these conditions are underneath here. Okay. You guys. The first condition is independent trials. So this comes from doing repeated independent trials. In other words, whether you got the first question correct, did that influence whether or not you got the second question correct? No, the second question is completely independent of the first one. Okay? And we did multiple trials. Okay. The next thing, we have a set number of trials. Did we have a set number of trials here? And what was our number of trials?
4.
4. Each question was a trial, yeah? All right? All right? Each trial needs to have the same probability of success. What was the probability you got the first one right? 0.2. What's the probability you got the second one right? 0.2. Are you guys with me that it's each question had the same? And the last one is that the trials, why can't I say it right now? The trials are binary, and what that really means are 2 possible outcomes. In other words, even though there were 5 choices for each question, the outcome itself was, did you get it right or wrong? We doing okay?
Yes.
All right. Now, let's pretend we don't have those numbers, okay? You with me? And then I asked you to find the probability x was greater than or equal to 2. You with me? Which means I want to find the sum of those 3 outcomes. Now, I happen to know that these outcomes are 8.18.
Oh, yeah.
You with me? Are you with me that these would have to be 1 minus that 0.818? Or however I,
Well, when I added it, it wasn't 1.
Was it close to 1?
It's like 1.2.
Then you got something wrong and I'll come take a look at it. Are you with me that the probabilities, if it's every possible outcome, the probability should add to 1. So if you can find everything else, then you do 1 minus to find that probability. So here are some of the symbols that we will be using quite a bit. There's lots of calculator stuff today. If you don't have your calculator out, now would be a really good time to get it out, because we're going to use it a ton.
Well, because I thought that I could see the board better from back there, but then I realized I couldn't see it anymore. It was far away now.
Yeah, of course. Sorry, didn't really should need one. All right. Okay. First things first. Symbols that you need to know. N is your, oh my gosh, I was about to write the wrong thing. N is your number of trials. Not unrelated to your sample size. Okay? P is your probability of success. Q, your probability of failure. And X is your number of successes. All right. Now, because there's always that known tree diagram pattern, your calculators are pre-programmed to find different binomial probabilities, okay? There's two functions in your calculator, and I'll tell you where they are in just a second. All right. The binom PDF will answer a question that is of the form, the probability x is equal to some number. Okay. So, for example, the probability that you got 2 right would be the probability x equals 2. Everybody good?
Yes.
All right. The binom CDF, also in your calculator, will find the probability x is less than or equal to some number. All right, consider rolling a dice 20 times. Let x equal the number of times we roll a 3. Well, does this meet those criteria to be binomial? So let's start with, do we have a set number of trials?
Yes.
So we know that n is equal to 20. Great. Do we have the same probability of success each time?
Yeah.
What's the probability you roll a 3?
1
Yes.
The 20 is the 20 helps us. No, like it's important that we kind of talk about this. There's the number of trials, and then there's the probability of each individual trial. So when we come up with that p, we're trying to find the probability of a singular trial. I roll my dice. What's the probability it comes up? Okay. Are those trials independent? In other words, when I roll a dice, and let's say I get a 3 the first time, does that change the probability of getting a 3 the second time? And is this so independent? Great. And is this a situation where we can map it as success and failure? Is it binary? Yeah. You roll a 3 or you don't roll a 3. So this is binomial. And the minute we know something's binomial, we can start using our calculator. Okay? So, in this particular case, what is the probability we roll a 3 exactly?
Means binomial? Or why'd you write binary?
Binary describes individual trials. The combination of all of 4 of these things lead us to say that this is a binomial variable. It has to, if all those 4 things are true, we can use the binomial distribution. All right. So this is when we're going to start using our calculator. All right. So we haven't really used this menu in the calculator yet, but we're going to start using it a lot. Okay. Your calculator is pre-programmed with known probability distributions. Okay? Anybody see anything that might help us with known probability distributions?
1 6.
I'm sorry?
Stat.
Distribution.
Do you guys see that there's a menu that says distributions? Is everybody okay? So go ahead and hit second and vars to bring up that menu. And you'll see there are a ton of probability distributions. In fact, one of those probably looks pretty darn familiar.
Window.
What are you doing?
I don't have that screen.
Normal PDF to normal
Oh,
PDF.
okay, because I had.
But this one isn't a normal distribution. We said it was something called a binomial. So let's just kind of do some scrolling.
Oh, probably A.
Are you guys with me? Okay, so if the distribution is binomial, we're going to be using one of these 2 things, either the binom PDF or the binom CDF.
PDF.
In this case, we want to find the probability that we roll exactly 4 3s. Yes? All right, so we are trying to find the probability that x is equal to 4. If we're trying to find the probability of equal to, we pick
C.
PDF. So, go ahead and choose option A. Yours is going to look a little bit different than mine, I would think. Does yours say trials?
Yeah.
What do you think you should put in for trials? 20, because that's how many trials we had, yes?
Yes.
Then it's asking for P,
4.
1, 6.
Oh.
1 divided by 6. Then it's asking for X. We're finding the probability X is equal to what number?
3. What? A second.
Is everybody with me?
0.2022.
Oh,
You're welcome, Shelby.
Okay. This next one, what is the probability we roll a 3 at most 3 times? How do I express at most? What does at most mean?
Greater than or equal to.
Excess or less than.
Less than or equal to 3. Because 3 is the biggest number it can be. X could be 3 or anything beneath it. All right, and if it is, X is less than or equal to 3, which option in the calculator are we going to pick? Binomial CDF. Oh, crap. Trials is 20. P is 1/6. X value is 3. Everybody good?
Why is that 5?
Hey, where's the 5 come into play with this?
Oh, you guys, it's 5. It's 5. No. X is 5.
Yeah.
Because X is your number of successes. My bad, y'all. All right. So if my problem is set up as an equal to or a less than or equal to, are you guys with me that this isn't bad at all? You just and you will eventually remember PDF versus CDF because we're gonna have a lot of time opportunities to practice it. Okay. All right. So now this next one is, what is the probability X is less than 8? First of all, you guys, is it going to be a big probability or a small probability?
Mine shows big. It's not
Really big because there's only numbers.
Well, getting less than or equal to 5 is 89%, right? Almost 90. It's practically 90. Yeah? And aren't there more outcomes that are less than 8 than are less than or equal to 5? So it's going to be bigger than this number. Now, that being said, I bet there's a nuance to this question that I want to make sure we understand.
It's less than.
When I put this into the calculator, my X number will not be 8.
7.
Why is it 7?
Less than 8.
Because it's less than or equal to. And this is a discrete random variable, yes? So whether or not I include the 8 or not is really important. Everybody with me?
Yes.
Okay. So to do this, we have to do the probability X is less than or equal to 7. Then we can go into that binomial CDF and turn it into a 7. And was my reasoning of we're adding more possible outcomes helping you guys understand that even this is a small number of the possible outcomes, right? 7 out of the possible 21 different outcomes, but it still accounts for almost all of it. Does that make sense to you in terms of the probability of rolling 23s in a row is way less likely, right? That there's all the low numbers are the ones we would expect to happen more frequently. Okay. What is the probability that we roll a 3 at least 7 times. At least would be x is greater than or equal to 7. What are we thinking?
Will it be the same?
More than 7 versus less than 7?
But it's more equal to it. So it is exact.
You guys, can we agree that less than or equal to 7 and greater than or equal to 7 mean two different things? So this one is the probability of getting 7, 6, 3, 4, 7, 6, 5, 4, 3, 2, 1, and 0 correct. This is me asking you to find the probability they get 7, 8, 9, 10, all the way up through 20 correct. They're not the same probability. That sign matters a lot. Is everybody with me so far?
Yes.
All right. Now, you want to do 8?
Like, it should, I don't know what we should do.
One option is we could do, you guys are going to choose not to do this option. I'm going to write it out. Don't write it down because you're not going to want to do it. We could find the probability x is equal to 8 and add to it the probability x equals 9 and add to that the probability x equals 10. Oh, and the probability x equals 7. Right, because it's greater than or equal to 7. That sounds really unappealing, yes? Is everybody with me? What if I found the probability of everything else and subtract from 1? Would that work for you guys? And what is everything else besides these outcomes?
Less than 7.
Less than 7. Yeah?
Listen.
So, and this is the hardest part about using these different distributions. The probability x is greater than or equal to 7 is equivalent to 1 minus the probability x is less than 7. Does this make sense? This is a huge, huge jump. And I can give you a visual representation with the previous question if you need it.
I need it.
Okay. You guys, by the way, doesn't that mean we have to do 1 minus the probability x is less than or equal to 6?
Yes.
Because we can't do strictly less than, we have to do less than or equal to. And then we do the binomial CDF. It is very, very common for kids to get this far, do the binomial CDF and not actually subtract their answer from 1. Do you guys know what I'm saying there? Like they plug it into the calculator and assume they're done. What happens when you plug this into the binomial CDF?
Wait, why'd you do 6?
Because we can't, that CDF can only do less than or equal to. So the outcomes that are less than 7, which is the opposite of greater than or equal to 7, right? The outcomes that are less than 7 are less than or equal to 6. What are we getting?
0.0371.
Oh, that's after you subtracted.
Yes. Oh, sorry. Well,
So that would have been 0.963,
yes.
which works out to be 0.037.
Wow.
Okay, let's look at this next one. Suppose 40% of statistics students will major in business. We take a random sample of 15 students. What's the probability that more than 10 of them will be business majors? All right. As we go to select our person, are you guys with me that every time we select a person, that is, in fact, a trial?
Yes.
So, how many trials do we have?
15.
And if it's 40%, if any given major business, stat student is a 40% chance of business major, we have that same probability of 0.4 for each student. So do we have a set number of trials? Are they independent from each other? And same probability of success each time. And binary, right? They're either a business major or they're not.
Yes.
All right, so this is binomial. And what probability do we want to find? More than 10. So anything with a greater than, anything, no matter what it is, you're going to do 1 minus the opposite. What is the opposite of a number being strictly greater than 10?
Greater than or equal to 9. Or, wait.
So here's the, you guys. So here's a thought process you go through in your head, okay? You guys, which outcomes are greater than 10? 11, 12, 13, 14, 15. What are the other outcomes?
9, 8, 7, 6.
10, 9, 8. Yeah?
Yes.
So, less than or equal to 10.
Goodness gracious.
Now, if you're looking at this and say, last time we took it down by 1, my last symbol was greater than or equal to 7. So which outcomes are greater than or equal to 7? 7, 8, 9, 10. What's everything else then? 6, 5, 4, 3. All right. Hey, from here, I like to, before I even touch my calculator, write down the 1 minus so I don't forget to do it. And then we just throw this into binom CDF. So what was the less than or equal to 10?
9906. I think.
No, that sounds about right. And then 1 minus that would be 0.0094, something like that. Yeah, so if it was 9906, that 6 was rounded one way or the other, and then
It wasn't rounded.
should it have rounded up?
Oh. You're right.
Are we good? All right, because binomial distributions have are known quantities, they also have a known mean and standard deviation formula. So you don't have to go in and type everything into the calculator like we did yesterday, right? Okay. If it follows, so yesterday we were talking about any kind of probability distribution. This is talking about a more specific version of a probability distribution. And you don't need to use all that. You just use these formulas, which, let's double check, are right here on the formula sheet you'll get to use on the test. Okay, so like you don't have to memorize these, you just need to be able to use them. All right, so let's go back to that previous example where we had n equals 15, p equals 0.4. And if I asked you to find the mean and the standard deviation, the mean would be 15 times 0.4. Six? Yeah? Remember, sometimes we call that mean the expected value. Okay, so we could think of this as we would expect to get 6 out of the 15 students in our sample to be business majors. Yeah? Okay. And then the standard deviation will be the square root of 15 times 0.4 times 0.6. That's it.
Why do you do 0.4 and 0.6?
Because the formula is the square root of NPQ. So remember, P is your probability of success and Q is your probability of failure. So, would it be unusual to get one business major in the sample? Help me remember, guys, from yesterday, how did we decide if something was unusual? More than 2 standard deviations from the mean. So let's come up with that interval real quick. We would do 6 plus or minus 2 standard deviations from the mean. So the usual amount of people in this sample that we could get is 2.2 to 9.8. All right, so 1 is unusual. 8 is usual. 14, unusual. All right, so now we're just going to talk about a different known distribution called the Poisson distribution. Poisson. For those of you who take French, the fish distribution. Okay. So, all right, so the Poisson distribution is the occurrence of some event over a specified interval. Is everybody with me? So, where X will be your number of successes, essentially. And it's going to be random. It's got to be random and independent. And then also, the occurrences need to be uniformly distributed. Think of that meaning evenly distributed over the whole interval. Usually that interval is a time span. Okay? So, the mean is going to be given to you in a Poisson situation. The standard deviation of a Poisson is the square root of whatever the mean is. Everybody good? Let's look at the less than or equal to 23 is, right? So it's going to be an example. The fish distribution? It's pretty good. Pretty good. All right. You guys, so suppose the mean number of tardies of Grandview students in a 5-day week is 58.8. Find the mean tardies per day and the standard deviation of the tardies per day. Did you guys catch the drift of this? Okay, so what would the mean per day be? 58.8 divided by 5. One. 11.76, great. And so then what would the standard deviation be? It would be the square root of that 11.76. Also, you guys, this formula is on your formula sheet as well. The standard deviation, so this is a Poisson situation because we have the time interval of a day of school. Everybody good? Okay. Would it be unusual for there to be 15 tardies in a day? We would do 11.76 plus 2 times that 3.429.
No.
Just the whole.
No.
You said yes and this.
It's no.
Yeah.
Because I forgot it was 2 times.
All right.
No, it would not be anything.
No.
That's insane.
What are we getting?
It's not good.
18.618.
So no.
Yeah.
Because 15 is less than. You guys didn't get 18.618?
I did.
That's what I got. That's what I got.
Okay.
Wait.
All right. Now, what if I ask you what is the probability that we get exactly 10 tardies in a day?
Would the trials be 58.8?
So, you guys, this does not follow a binomial distribution because
It's Poisson. Oh.
because we don't have a set number of trials, right? Like we're trying to count how often something occurs in a time period. Okay? So, you're going to go to that distributions menu. And if you scroll down past the binomial, you're going to see a Poisson distribution where you still have PDF and CDF. Okay, if I'm finding the probability that x is equal to 10, which one do I pick?
PDF.
PDF.
Distribution. Stop. Get away from my computer.
What is that?
Calculator.
58.8. Oh. 10.
I would assume you put in. What does it ask for? Lambda?
Yeah.
Put in
58.8.
put in the mean. So 11.76 because this is in one day. Yes.
10%. 89.
No.
So, you guys, the difficult part about these is there's 2 parts of this that I think are where the cognitive work happens. Okay, first of all, are we talking about something that's binomial? Are we talking about something that's Poisson? Okay, so knowing which one of those two things is correct. If it's a time period, it's Poisson. If it's a set number of trials, it is binomial. Okay? And then the other part is picking the PDF versus CDF and doing that correctly. Okay? So let's look at this next one. Same context. What is the probability that more than 15 tardies occur? Are you guys with me? That means the probability X is greater than 15.
Yes.
Okay.
Just make that 16.
No.
We got to think about this, you guys, okay? Which outcomes are greater
16.
than 15? 16, 17, 18, blah, 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 blah. Technically up for a large number. Which outcomes then are not greater than 15? 15 and below, so you're going to do 1 minus. The probability X is less than or equal to 15. So then we do Poisson CDF. 11.76, and then and 15.
If you turn my calculator off one more time, I will beat you on the head with it.
Do I need to separate you two?
He keeps turning my calculator off. Mid-problem.
So sorry.
No, you're not.
You're just
Stop.
so I can play him.
All right, let's look at the next one. All right, so you guys, when I ask you what is the distribution, that's usually like give me the name and the important characteristics. Okay, so if we look at this one, the 20 calls are received in the customer service center between 9 a.m. and 10 a.m. on average. The minute I see that 9 a.m. to 10 a.m., you should say, oh, this is Poisson, with the mean equaling 20. And the standard deviation equaling the square root of 20. Which I'm assuming is like 4.5-ish. 4.47. Close.
The distribution, just the standard deviation.
It's both. It's like the name and then the... Okay. What is the probability that the call center gets fewer than 14 calls between 9 a.m. and 10 a.m.? Sweet. So we're finding the probability X is less than 14. Does that fit one of my calculator functions? No. Because the CDF is not less than, it is less than or equal to.
I'm getting scared.
1 minus the probability X is less than or equal to
14.
13.
Oh, gosh. No.
Oh, no, it's not 1 minus.
Oh, my God.
It's just the probability X is less than or equal to 13. What are we getting?
0.065.
0.065?
66.
Cool.
Half the probability. Exactly.
Oh, exactly.
Okay. Next one, what is the probability? Obviously, that's meant to say what, not hat is the probability that the center gets exactly 22 calls.
Yes.
So we're finding in this case the probability x equals 22, which is a
PDF.
PDF. Throw it into the Poisson PDF.
That's the best one we got. 0.077. You're welcome, man. Wow, this next one's good.
Don't think I did that right.
You guys, if the mean number of calls between 9 and 10 is 20, yeah? What is the mean between 9 and 9:30? Are you guys with me that if we shrink that period, we have to kind of think through? So now we're finding the probability x is at least would be greater than or equal to, yeah? That means 24 is the lowest. You guys, using your gut, is this going to be a big number or a small number? The mean is what we would expect. We'd expect them to get 10 calls. 22 is going to be a ton, yeah? All right, so this one we're going to have to do a 1 minus. Okay. You guys, which outcomes are greater than or equal to 24?
X is less than or equal to 23.
It would be 24, 25, 26. So which ones are not?
23.
So this one we're going to do 1 minus the probability x is less than or equal to 23.
Oh my god,
It's like it's 1.2 times 10 to the negative 4.
Just take a second.
Okay, are you guys with me
Going towards X, then
that if we're doing 1 minus, we're essentially thinking about this as that every outcome occurs exactly 1 time, so that all the probabilities add up to 1. Is everybody with me? All right. So when we're looking at this one, has the 15 occurred in the x is greater than 15? Are we including the 15 here?
Oh.
No. So if I'm not including it here, I have to include it here.
okay.
Whereas on this one, am I including the 24 here? So I can't include it here.
Okay. I think I get it. A second to think about it. Just need to think
Is that what it is?
yeah, 0.999.
Well, 1 minus the 0.999. So
Would it be acceptable for regular scientific notation if it's a small sample?
if it gets small enough, yeah.
Because I got like 1.2 times 10 to the negative 4.
If it like negative fourth, I would prefer that you
Right.
move it over,
Okay.
but
Then I use 10. 10. No. Wait. What? No. I know. I thought I just put that.
And then for this one, it would just be the mean is 5.
okay. So, yep. For this one, the mean is going to equal 5. We want to find the probability. At most 11 would be less than or equal to 11. Since it's in that less than or equal to form, you just throw it in. to the Poisson CDF.